Hey guys, in this video we are going to explore the concept of balancing chemical reaction equations. So to start things off, let's introduce a quick definition here. So the definition of a balanced chemical reaction equation is a chemical reaction equation where you have equal numbers of each type of atom on both the reactant and product side, right? And the two main methods for accomplishing balancing of a chemical reaction equation is either the whack-a-mole approach or the algebraic method. Now, in this video, we are going to focus on this first approach, the whack-a-mole method. And once you get one approach down, you really don't need the other one. So this will be an optional video that you can watch afterwards. So the idea here is, given a chemical reaction equation, we want to be able to come up with these stoichiometric coefficients such that if you add up all the different atom types on both sides of the equation, right, then you will end up at the end of the day with the same number of each atom type on both the left-hand side and the right-hand side. So we can see with this example right here that we are in fact balanced by having these stoichiometric coefficients of 2 in front of H2 and H2O in our formation of water reaction. And so this guiding principle is a manifestation of the so-called law of conservation of mass, which states that if you are working in an isolated system, you can't create or destroy mass. In other words, assuming atoms aren't changing to different types of atoms, there's no nuclear chemistry, no nuclear physics happening, right? You are going to end up with the products that have the same number of individual atoms as you did when you went in on the reactant side. And so for the purposes of this class, we are not going to consider any sort of transformations where you involve changing the elemental identity. So any sort of nuclear decay, nuclear reactions, we're not going to talk about that. And we're not going to consider any sort of mass changes that would then occur alongside these transmutations of the elements. So we're not worrying about Newton stuff. All we are doing is simply counting up the number of atoms of each type on both the left-hand side, reactant side, and the product side, right? And the mass of each and the total number of each, therefore must be equivalent. Hey, so with this law of conservation of mass as serving as a sort of guiding principle here, the technique then really comes down to figuring out what set of stoichiometric coefficients, denoted here in orange, right, we need in order to ensure that mass is in fact conserved. So the first thing we're going to do here is jump into that whack-a-mole approach for accomplishing this task. All right, so the first step in balancing a chemical reaction equation using the whack-a-mole method is to basically write a line right down the center, separating products and reactants, and essentially build a little table that will allow you to quickly and efficiently represent tallies of how many of each atom type are present on both the reactant and product side. So in this case, if we look at the decomposition of water, H2O going to H2 and O2, right, as written, we have only 2 hydrogen atoms and 1 oxygen atom on the left-hand side. And on the right-hand side, we have 2 hydrogens and 2 oxygen atoms. So what that means is that these hydrogen atoms are already balanced, right? However, we have an asymmetry in the number of oxygen atoms. So what we need to do then is ask ourselves, what sort of stoichiometric coefficient can I add in order to get this guy to end up at 2? We need 2 oxygen atoms. Well, hopefully you guys will see that by simply introducing a stoichiometric coefficient of 2 in front of that water molecule, we will have effectively balanced the number of oxygen atoms. All right? Now, it's important to note that once you introduce that stoichiometric coefficient of 2, yes, you have changed the number of oxygen atoms so that those are now matching. However, you have also changed the number of hydrogen atoms. We now have a total of 4 hydrogen atoms on the left-hand side. So in the course of balancing one of these atom types, we've effectively unbalanced one of the other ones that was previously balanced, hydrogen in this case. And that is the reason why I like to call this approach the whack-a-mole method, after the game where you basically have that little mallet and you whack the moles as they pop up. So we saw in this previous step that we needed to balance oxygen, so we balanced oxygen, that was the mole we whacked, but then in whacking that mole, another one popped up, hydrogen, okay? And so what we're going to have to do now is introduce another stoichiometric coefficient in order to get this side to match up. And of course, that's going to be carried out by introducing another stoichiometric coefficient of 2. And so that will be our next mole to whack, will be our hydrogen there. So introduce that stoichiometric coefficient of 2. We then have 4 hydrogen atoms on the right-hand side, 4 on the left-hand side. And because this element showed up by itself here, H2, there's only hydrogen present, introducing that stoichiometric coefficient does not unbalance the number of oxygen atoms, so we are in fact all set and ready to go. So to sum up this process, the whack-a-mole approach, first step is to determine the total number of atoms on both reactant and product side, determine which atom types are unbalanced, and then pick an unbalanced atom type, change that stoichiometric coefficient to balance the atom, and simply repeat the process until all atoms are balanced, until you've whacked all of the moles. Okay, so a general approach along those lines will eventually solve the problem one way or the other, okay? But it turns out that there's some hints that I can give you to essentially speed up this process and make your work a little bit more efficient. And really what that comes down to is this third step here in terms of picking the unbalanced atom type, and it's kind of moving forward from there. Which one do you pick first, in other words, if you have more than one? Okay, so to see this in action, rather than say it, I want to show you an example. Let's look at the combustion of propane. Okay, so we have CH3H8 reacting with oxygen to form CO2 and water. So setting up our little tallies, we see that we have 3 carbons, 8 hydrogens, 2 oxygens on the reactant side, 1 carbon, 2 hydrogens, and 3 oxygens on that product side. Okay, so the first hint in picking which atom type to balance, because notice in this case all 3 of them are unbalanced, is I'm going to tell you to go ahead and leave hydrogen and oxygen for last. Okay, leave hydrogen and oxygen for last and go ahead and balance that carbon atom first. So balancing carbon requires the introduction of a stoichiometric coefficient of 3 in front of that CO2 on the product side. But notice that introducing a 3 changes not only the number of carbon atoms, but also the number of oxygen atoms, okay? Because it's 3 of those entire CO2 molecules, right? But once we've introduced that and taken into account the changes in the number of oxygen atoms as well, we've effectively balanced our carbon atoms. Okay, now we can come in and balance our hydrogen and oxygen. Now here's the second hint. I'm going to tell you to balance hydrogen first, okay? And the reason being is because if you save oxygen for last, you can introduce whatever stoichiometric coefficient you want right here, and it won't unbalance any of the other atom types, right? So focusing on that hydrogen first, we can introduce a coefficient of 4 in order to get a total of 8 hydrogens on the right-hand side. And of course, once again, because we have changed that coefficient in front of the H2O molecule, we now have a total of 4 oxygens coming from the 4 waters and 6 oxygens coming from the 3 CO2s, giving us a total of 10 oxygens on that product side. Okay, then as a last step, we can come in and introduce that stoichiometric coefficient, in this case of 5, in front of that oxygen atom, and we can safely do that, balance oxygen, and once again, not perturb any of the other atom type numbers, because in our O2 molecule, oxygen is the only element, okay? And so that's our guiding rule here. Basically, if you have an atom type that's showing up in a molecule on either the reactant or product side, and it is the only atom type present, then save that guy for last, right? Because you save it for last and you're guaranteed for it to be the very last step because you won't mess up any of the other balanced atom types. Okay, and so that summarizes the so-called whack-a-mole method. In the next video, optional video, I'm going to introduce another technique that you can use, which basically, removes the guess and check work and just forms the whole balancing of a chemical reaction problem in the guise of a set of system of equations. So basically turn it into a simple algebra problem.